Thank you very much. Today I will talk about the challenges, one challenge in particular that I faced when I joined the Ferrari Formula One team. And I'll talk about 4 pieces of the solutions of that challenge. My name is Luca. I have a technical background, 20 years of experience in professional software development. That is my company, but mainly today I will talk about my experience with one of my clients, the Ferrari Formula One team. So I joined Ferrari in 2006. We won a driver championship with Raikkonen. We lose a driver championship at the last corner of the last lap of the last race of the season with Massa. But if you like Hamilton, you are happy about that. We also won 2 constructor titles. And when I joined the team, I initially started to learn about the different type of softwares that are used there. There is a software that is used to design and develop the car in between seasons and during the seasons. There is software that is used to prepare for the race and software that is used during the race weekend. And then there is software that runs inside the car, on the pit wall, and at the home factory. And then when I joined the team, my boss told me, this is what you have to do. You need to help us to make software development go faster and at the same time safer and more reliable. You have been hired as an expert, so you need to help us doing that. Oh my God. I was hired as an expert and I didn't know how to do that. Then I get to know the team and I realized that everyone else in the team was an expert. What a humbling experience for me. We had Neil Conzen. If you watch some movie about Silicon Valley, the fight between Apple and Microsoft to deliver the first operating system with the graphical user interface, and they were fighting about that, he is the Microsoft guy that managed to deliver Windows. And then at some point we were trying to step up and to improve our approach to test-driven development and continuous delivery. And a guy that worked with the Connextra team, Paolo Polce, joined us. If you don't know about Connextra team, has been one of the first team in Europe doing extreme programming. A lot of things has been invented there, and probably in your team there are some practices that you are using today that has been invented in that team. And Connextra is and was from London. So there was a lot of interesting people there. Like in every professional software development endeavor, there are challenges and constraints. That was for sure not a greenfield type of project, and we had some constraints. But in retrospective, some of those constraints actually helped me and helped the team to find some of the pieces of the solution. So I want to start to share with you some of those constraints. Well, the Formula One sporting calendar is inescapable. There are a limited and well-defined number of test and race events. The date and the location is fixed, and you cannot move them. And there are systems, software system and other infrastructure that are available only during those events. So you want to maximize your chances to test your software during those events using those systems. Most of the features are developed between one race and the other, but some big features, some feature change request may span multiple races. So you will ideally try to make the best use of those systems available at the official events. The second constraint was about remediation plans, automatic remediation plans. Actually, guys in the software development team, they were very smart guys, and they had this possibility. At any moment during the race or during a qualified session free practice, as soon as they face a showstopper bug, they can, with one click, roll back an application instantly to the previous stable version. So something bad is happening, no problem. One click and everything go back normal. Maybe you lose the latest feature, but still you can go ahead and continue to do your job. And that's important because some of the software is mission and life critical. Some software is used to ensure safety of the driver and inform driver of problems before it's too late. One of those applications had a programmed expire date for security reason, to protect the intellectual property in a special moment during the championship. So you could not roll back that application. And that was an example of an application that has a backward compatibility problem. The new version of the application, once it's expired, you cannot go back to the previous version. So this challenge enables us to find a way to deal with automatic remediation plan, even when you have changes that break backward compatibility. And finally, there was an unexpected event, a problem. Our source control had a bug that prevented us to merge, or we could do merge, but the result was not exactly as expected. There was no time to switch to a different source code repository during the championship. We had that in plan, but we couldn't do that fast enough. So guys, from now, you cannot use branches. As you will see, actually, that was very useful to point us in the direction of the solution. So let's start. Now I'm going to show you 4 pieces of that solution that we found. I realized an extremely simplified version of a real application that simulates the lap time is used to decide the strategy for the pit stop. So I've created an extremely simplified version that shows the problems, and I can use that application to introduce the solution and to demonstrate the solution. So now let's talk about lap time simulation. And what is it? Basically, we want to take into account the ideal lap time of the driver, the best lap time that the driver can do, and take into account the degradation of the tires. The tires wear out lap after lap, and so the car gets slower. And take into account the fuel. The fuel is heavy and slow down the car. So all these ingredients help us to calculate the real lap time. And then there are other things like overtaking and so on. The real application take into account all these elements to simulate all the lap type and all the race. And with that information, race engineers decide the pit stop strategy. This is a simplified version, so we only take into account the tire degradation. We don't take into account fuel and overtaking. And for this extremely simplified application, so we ask some data that I will explain soon, and we calculate the lap time of a few laps. That's the sample application. Let's see how it works. A quick demo. Just make it run. So they're asking me what is the ideal lap time of the driver, how many seconds the car gets slower because the tires wear out at each lap. And here are 4 simulated lap time. So now let's see what's the logic behind it. So here we have the lap time. During free practice and qualify session, the drivers try the car, and every driver gets his own ideal lap time. At every lap, the tires wear out. And there is a function that describes the degradation of the tire. For this example, the function is a very linear one, like you saw in the demo application. A few seconds, everyone are lost. The real function is not that simple at all. So you see that at every lap, the lap time increases, the car gets slower, right? This is what the application is calculating. If we look at the source code, there are some parameters that are used. For now, we are talking about two parameters: the ideal lap time and how many seconds the tire make the car go slower every lap. Then we have a simulation that takes those two numbers into account and tell us what is the actual lap time at each lap. Storage, where we can store the previous data. We have the storage, and we have a program that is wiring everything, is retrieving the simulation parameter, is dealing with the UI to ask input and write the result, and finally is storing the last simulation parameter, in this case just to make data entry easier. Could be the database, could be something on the cloud. Something interesting to say is that in Formula One there are different types of application. You have a client-server application, you have distributed application, database that are accessed remotely, or travel database servers that travel with the car at different tracks even. The blood of the software in Formula One is the telemetry. So there is a lot of telemetry and a lot of data. There are race engineers that run simulations about the performance of the car, or simply aerodynamic simulations or lap time simulation. And they use tools like MATLAB or Simulink. And sometimes they use tools like Excel. They try something new connected with actual data, and if things actually are useful, they say, okay, now let's develop a real application. But they experiment and use those tools. In general, there is a lot of comparison. Something that race engineers do a lot is to compare different laps. They change the setup of the car and they see if things get better or not. And they compare the lap time from this year to the previous year, or from one tire set and another. So there are a lot of compare going on there. The storage here in this sample is interesting because it's one of the ingredients that simulate compatibility braking changes. But overall, all the patterns that we found that were part of this solution will work even if you are developing a mobile application, a web application, an application in the cloud, on AWS, a serverless application, and so on. So what we are discussing today is not bounded to the type of software that we used in that environment. And we discovered that in the following years. This was about 10 years ago. So here we are. We have the first version of the application, the one that I just demoed to you, and we have a version of the database. I call it version number 10. It's a simulation. We are really storing two parameters. The real one is different. They have much more parameters about the tire degradation and so on. So what happened next? Well, we have a new feature request. What a surprise. A race is coming. Some race engineers say we want to improve our simulation of the tire degradation, and we want to take into account a new parameter, the temperature. Tires actually behaves in different way. The grip, the actual grip change based on the temperature of the track. And we want to develop these features. We may be able to finish it in time for the next race or not. And remember, we cannot use branches, and anytime someone may need to use that source code to fix a bug or to release another feature, even if our feature is not already completed. So how it works? the tire operating temperature? Well, there is again ideal temperature. Reality is it's a window, but for this simplification is good enough. And at that ideal temperature, we have the best performance of the tire and so of the car, right? As soon as the temperature move left or right, it becomes hotter or colder, the performance of the tires go down and the lap time goes up. Again, we are using a linear function here to make things simpler. So that's what we have to do. Let me go to the code and show you some example. So the current version of the system have the two parameters that I mentioned before. Here they are, the parameters of the simulation. And then we have an extremely simplified simulation. We get the two parameters in the constructor, and then as input we use the lap time, and using the formula that I showed before, we calculate the real lap time using the degradation, the number of lap, and the ideal lap time. How can we start to develop, start to introduce code for the new formula of the simulation without breaking the current application? How can we do that? So now we are a little in hurry, so I will skip ahead. Oh, let me show you that here we have all the unit tests, acceptance test, integration test, and the normal test with everything. Yes, we wrote and we used test. In that case, I will skip ahead and I will show you what was the first step. So the first step was to introduce side by side the new formula that now take an additional parameter, the tire operating, so the delta from the ideal temperature that actually the driver is facing at the lap time. And the new formula uses the ideal lap time, the degradation per lap, and also now uses the delta, that is the additional parameter of the simulation, with the delta of the actual temperature. Here the real trick is to start to introduce the feature, the new function side by side. Who is using this function? No one. Only the test so far. But the source code is releasable. We can commit the code, we can release the application, and at least we are start to testing it. I'm intentionally showing you small steps. I'm breaking down a big development in small steps, not because you are slow to follow me, but because actually that is by design. Every small step, all the tests run and we get some feedback. Every small step can be deployed in production, so we don't stop that possibility. So that is the first step. And then you can see we have tests here, as I was mentioning before, that start to use that feature, only in tests for now. Let's see if the demo effect is there or if things actually work. Everything is working. So let's quickly go back. That was a very small step, right? What we did in this small step, I'm introducing you two patterns, trunk-based development and latent code. Trunk-based development means that we are not using branches. We are committing directly on the main line. Software that is in a releasable state. That's the first pattern that is very well known nowadays and enabled us to have very quick, early and quick feedback. And that was good because the later, the harder it is to fix things. And the second is latent code. So we start to introduce code that is used only by automatic test, is latent. is deployed into the binary, but is not used. Just a small step. Let's move to the next one. Okay, now we want to do something more. The race is approaching and the feature is not finished. This was a very difficult one, not the sample application, the real one. So how can we take advantage of the production systems? How can we take advantage of those systems that runs for real only during the races? Making the most of the limited number of tests and race event. So what can we do next? Of course, we are implementing the new mathematical model. We will need to implement and update the user interface and also the storage. But for now, we are dealing with the mathematical model. What can we do? How can we start to take advantage of the next release of the software that is going to be used into production during the race? Do you have any idea? Can you think about anything? I show you what we did in this case. So we start to say, okay, but we can run the new mathematical model using a special value, and so the original mathematical model will continue to function properly, right? If we said that there is no delta from the ideal tire temperature, this part of the equation will go away and it will behave as before. So we are start to putting in use the new code in a special case, but is more than nothing. So now, not only the special tests that we wrote before are using the new code, not only the new tests that I showed you before now are using the new code, but all the previous tests are using the new code. So now when I run, what I'm learning? Well, from the development or test environment, I'm learning that the new feature is not breaking the existing test. But I can deploy this application. I can use this application during the race, and I can see that everything is continuing to work as before, or I can identify a bug, and with one click, I can roll back, no problem to race engineers, and we learned about the problem. So we can fix it immediately, and we don't lose a race next time. Everything clear? I would like this test to run. They run, so it really works. What have we done now? Which pattern have we introduced? So we still have a new version. It is backward compatible. We can roll back to the previous version as long as we use the previous version long enough to declare it as official, and the database is still the old one. But we have introduced a new code pattern that is about gradually putting in use code that before was latent, incomplete, but still we are putting it in use. And we are verifying that we are not breaking everything. So we are taking advantage of feedback from production early. Remember, you have the ability to roll back with one click, so the cost is 0. But if you wait, when you have the last version of the application with the actual feature and you discover a bug, at that time you will lose that feature for the race. So now, with this pattern, we gained a competitive advantage. You may think, yes, but in my business, it's not like in Formula One. We don't have a limited number of races. I think this is what many businesses sometimes miss. You have a limited number of hours per day. You have a limited number of days per week. And the companies usually have a limited time. So every time that you save time is important. It's just that Formula One make it crystal clear that you are missing an opportunity. So that's why those things are extremely important and useful even in your business. So the next step is, of course, introducing the user interface and the storage. Who suggested the feature toggle before? Yeah, so new user interface, new storage. But here the storage is the piece that we are simulating to break the backward compatibility. We have a table that contains the parameters of the function, but the new feature actually requires another table with all the data pointer. Now we cannot use functions. That functions are so complicated that we cannot just use parameters. We need to sample and calculate up front the value for every lap. So basically we save a sample of that function, and we need to have two tables with one row referring multiple rows. And the table is so big that you cannot roll back that easily with one click because it will take too much time. So the first step, as you suggested, is to introduce feature toggles. Are you familiar with feature toggles? Can you raise your hand if you are familiar? So I will try to go very quick for those who are not. In its extremely simplest form is simply a configuration value on a file that turn the new user interface and the new database storage on or off. If I build this and I run it, so let me show you the test. Here you see that some tests ran and some tests didn't. And I switch the feature toggle here. I run the tests again. In production is exactly the same. If I run the application, now the feature toggle of the application is false. If I put it true, we will have the new version. Oh, what's happening here? Do you know what's happening? Why we just had the runtime error? Can you guess?
You have to update database.
The backward compatibility. That's right. So this is exactly what would happen if we try to roll back this version. Now they're telling me how much time do we lose when we have a delta of the ideal temperature. How far are we from the ideal temperature? 9 degrees, and now I have the calculation. But if I go back, I will have a runtime error because we are changing the DB schema. And we cannot roll back that because you know that some database cannot roll back database changes. This is just an example, again, just to show an example of a database change. Now, let's quickly go back to the presentation. And here we are. We are running a version that still compatible, has a previous version that we can roll back to, and is still using the old database, as long as we keep the feature toggle off. And for those that are not familiar, this is a description of the feature toggle. So far we described two patterns that are well known, trunk-based development and feature toggle, and one pattern that is less known, latent to live code pattern. So let's see what's next. Now we want to put in production the feature. The UE is ready, the new data storage is ready, the mathematical function, we did it as a first step. But if we release now this feature, we lose the ability to roll back. How can we manage that? We don't want to do that because it's really cool that we can feel extremely comfortable, and if something goes wrong, we are still on the safe side. How can we do that? It's like crossing a bridge, a river, and when you are on the other side, you cannot go back. Instead, we want to do something that enables us to go on the other side, version 11, and safely go back. What is backward compatibility in the end? When can we break backward compatibility? At least we need two moving parts to have a problem with backward compatibility. An application and some document or some information stored locally or somewhere. Or an application and a service that change the interface and maintain some state. We always need two moving parts in order to potentially break backward compatibility. For example, an application and a config file. Your new version introduce a new format of the config file. Then you roll back and you had the runtime error like I had before. Document, new version of Word with the new document format. Well, they enable you to read both versions, but if you didn't get that, you won't be able to read the old documents. Or when you roll back, a web application and a database, well, that's what we are simulating here. We are changing the database schema with a change that is not easy to revert. An application and a component. Well, you're probably using containers, but maybe there is some server that is still running on Hyron, and you have a component that is global to that server. When you change that component with the new incompatible version, a new interface, all the applications that are using that component cannot run against the new one or against the old one. And same things with the service when the API change. When it's difficult, when it gets difficult to roll back changes, because those are backwardly compatible breaking changes, but let's start to see when things get difficult. When you have many documents and they are shared among many applications. I'm not talking about the user, many users that use the same application, but many different applications, each one used by many users, that access shared documents. Handling these breaking changes start to become difficult when you have a shared database and many, many different web applications using that tables. So one small change, nothing can be rolled back again. When you have a global component and many different applications using that component, or when you have a shared service and many different client applications. So this is when dealing with breaking changes become hard. What is the easiest way to deal with breaking changes? First rule, avoid the breaking changes. It can be done, and when you realize that, it can be done more often than not. Is that when we are young, sometimes introducing some breaking changes enable us to move to the next technology, to delete some code that is terrible, to start to do something really interesting and stop feeling the pain. But sometimes we just don't realize the cost of that breaking changes. And when we realize that, the pain that we are introducing, we decide not to introduce that. This worked many times. Another smart thing, run both versions of the application so you can keep both applications running, the old one and the new one. So if the new one stops working, you still have the old one running, or some user can use the old one. If you are familiar with the branch by abstraction, that's kind of similar concept, enable you to quickly switch between two versions. Keep both versions of the data. So for a while, you will save the document using both formats. So if the application stops working, you can roll back to the old one. Another trick, blue-green deployment and event sourcing is a technique that enables you to roll back. And with event sourcing, you can quickly catch back all the event and data that happen between your release and since when you face a showstopper bug. Or two-way live data migration. So make the migration not a big bang thing, but something that happened live. So Facebook introduced this, and when you have a lot of data, instead of having a big bang, the data can flow, but not only from the old database schema to the new one, but also backward if needed. Nice. Still, there are situations like our expire date and other situations like this sample application where you cannot do that, because avoiding the breaking changes is too complex. Sometimes it happens. The application is mission or life critical, so you cannot have downtime, and maybe some of the techniques that we mentioned before requires downtime. The data and the document are a single source of truth, so you cannot duplicate them. Or the application must be unique, because again, they are a single source of truth. Or you need uniformity on data, because you need to do a lot of compare, like we had to do in Formula One, right? A lot of compare with lap and setup. So here we are. We have a river, and we need to jump on the other side, and there is no bridge. We cannot go back. How can we do that? So we are late, and I will try to go as fast as possible. Here is the trick. We already had the feature toggle, but we did two things. We have two moving parts. So we already had the feature toggle, and the application can behave in both ways. We have two moving parts. We decided which moving parts is harder to move and which one is easier. And with the harder, I mean which one is more likely to hide the bug, and which one is extremely simpler. Instead, we feel comfortable that the bug will not be on that part. And in this case, it was the database. We were feeling comfortable that we could test the database. The bug will rather be on the application side and not on the database. So we decided that we want to make the application be able to support multiple versions. So it is forward compatible. It's supporting database version number 10 and database version number 11. The application automatically detects the current version of the database and set the feature toggle, or actually, it's not a feature toggle anymore. It's a self-configuring application. So the application detects the database and decides if they are in the old mode or in the new mode. Here we are. So this is supporting both versions. The new application actually supports both versions at runtime, but is released with the old database. So we have this forward compatible interim version, and let me share with you the definition. Please raise your hand when you finish reading. So here we are. We have this version that supports both, but we release this version with this database. The second step now, we release the same version, but with the scripts that updated the database. This is the step that we feel more comfortable. In what sense? In the sense that it's very unlikely in this specific case that bugs will be in the schema of the new database. And if there is something wrong that happened into production, we will detect that immediately when we run the application the first time. That's the assumption. This is where we choose which of the two parts. So we release again this version, this time with the new version. And still, if something goes wrong, we can roll back quickly to the old copy of the database because the application is self-configuring. So again, this is the forward compatible interim version pattern. Now, I want to tell you why we are almost done, why this is important. I show you a specific case of a pattern that can be applied in a much larger number of cases. You saw the comment about how many cases can create breaking changes. But there is a concept that is much, much deeper. Forward compatible enable you to tame irreversibility, but irreversibility is one of the primary drivers in complexity in software development, and complexity drives cost and risk. Enrico Zaninotto, an economy professor, made a study in economic systems about how irreversibility drives cost, risk, and complexity. And what we want to do in software development is to avoid irreversibility. Compatibility breaking changes actually is an example of something that is irreversible. You cannot go back. And that creates problem. And you know that because when you do the release, you're not relaxed, you are nervous. And what happens when we reduce risk? Who has an automatic remediation plan in place? Do you have in your organization an automatic remediation plan, the ability to roll back with one click? So, guys, you are lucky. I think you will feel like this picture on the right. Developing software can be boring, like resolving a puzzle. But for everyone else, when you do something difficult, releasing becomes like this. Extremely risky, exciting, but also scary. Instead, when you have the ability to roll back, you can achieve the challenge that I faced in front of me when I joined the Formula One team. How can we go faster and safer at the same time? Here we can do that. Here there is no chance. And here you can become more productive, faster, and safer. So I skip these details. On the left, you have an example of a graph provided online by McLaren, so I won't get arrested to show you this. Here you have two different lap times. This is not about tire degradation, it's about fuel. So you see that the lap time of the first car become smaller. The car is faster because there is less fuel on board, so it goes faster. The other cars start with less fuel, but then they have to do a pit stop, and then they start to go at the same speed. And instead, this is a cumulative gap between the leader of the race and the other driver. And here you see when there is some overtaking. So the real application give information like this about to the race engineers. So to finish, we had a look at 4 coding patterns, 2 that are well known, trunk-based and feature toggle, and 2 that are relatively unknown today, even if we did that 10 years ago. And when talking about latent to live code pattern and forward compatible interim versions that enable you to have automatic remediation plan even with compatibility breaking changes. So this pattern enables us to go faster and safer at the same time without the need to trade off safety for speed. And that's it. Thank you.